I'd really wanted already to talk today about the vital importance of building performance expertise, but last week's release of the Grenfell report has made that discussion even more timely. A lot of what happens revealed a toxic approach to buildings related to climate action, and that feels even more shocking once you realize, by looking back at the fundamental science, that the basis for demanding insulation is in itself radically flawed. It's clear the construction sector is in dire need of deep reform, and I think we here must be all of the same opinion. This means going back to first principles in building performance and taking a much broader view of what that requires, because essentially it means looking not just at what's happening in terms of the envelope and the weather, but also crucially, vitally incorporating the people into the equation, the ways the building's being used, what the occupants are doing to support all those uses, because there's never just one occupant or just one use. There's a lot of important science behind all of this, the physics and the material science, of course, but also very much the biology, the medical science. Alas, as we've seen in the Grenfell report, we live in a world that has a strong tendency to conflate or even replace science with technology, with new toys, even though they're not the same thing at all. So at the risk of teaching many of you here today to suck eggs, this morning I'm going to strip back to basics on some of that science to show how it explains why the use of energy keeps skyrocketing despite all those dangerous policy initiatives that were meant to bring it down. And of course, it makes clear why building performance professionals have a critical role to play in reversing that. I expect the medical science, at least, will be new to many people, although I guess also it really should have been our bread and butter as BP experts. Why it isn't, why it got siloed into medicine and ignored in building science, is kind of revealed by the third aspect we need to include, which on top of the science of the building envelope and of the people, we also have to understand the background history if we want to see what's been going on and why. As specialists in building pathology, of course, we're all used to some extent to the importance of history. All of us know that the first thing to find out to understand patterns of deterioration is what's happened to the building in the past. We're also incredibly lucky to get the chance of working on buildings of all ages, from the very old to the very new. And that gives us an important familiarity that's really rare with materials and structures that are different to the glass facades that now dominate, and also a deep respect for just how good those older buildings can be. What I do want to stress, though, is that when people generally talk about older buildings, they seem to be thinking of these. But for me, these are all pretty recent. I want us to go much further back into what we might call the pre-carbon built environment, when energy was seriously expensive and it certainly wasn't on tap. And that made all the difference, not just to the choices of material and design, but even more importantly to how the buildings were meant to be operated. If you know from actual experience just how much energy it takes to prepare materials, to draw water, to make a rushlight, you don't waste. And it's waste that's clearly central to pretty much all our problems. The deluge of fossil fuels and the miracle of energy and water at the flick of a switch quickly eclipsed hundreds, if not thousands of years of knowledge of construction and operation, and especially vernacular knowledge. And now we're paying the price for forgetting all the things that we used to know, not just in terms of climate change and all the other many self-inflicted catastrophes that are now making us feel like rabbits in the headlights, but also in terms of our own health and well-being. Because as we know, the siloing of expertise seems to be getting worse and worse, but the built environment is complex. And so many of the things that matter most just fall into the cracks between those silos. That's in a nutshell what makes building performance assessments so powerful. We all come to this from disparate backgrounds, and that wide viewpoint's exactly what's needed. Currently, the building sector as a whole just keeps focusing in on all those details, all the individual bits of the puzzle. But that's like a whole series of close-up snapshots, and nobody knows what anything has to do with anything else. But if we can get everyone to take a step back and look at the bigger picture more widely, more holistically, and really think about the underlying history and science, the whole panorama, if you like, then all of a sudden it takes on a different form, and it's possible to see how everything actually interacts with everything else to make a coherent picture. So let's get stuck into that. I'll get some of the basic building science out of the way first because it affects everything else. First and foremost, there are two basic and fundamentally different ways you can make an envelope that keeps out the weather and especially the rain. And it's perhaps not surprising, they more or less equate with pre-carbon, pre-industrial, and post-carbon, the buildings that are based on materials and structures that require lots of energy to make and to run. The old head of the Building Research Station in the UK in the 1950s, my hero Fred Masham-Lee, brilliantly christened them in-house greatcoats and raincoats. And I've stolen his idea, which he doesn't seem to have ever published, unfortunately, because these names are terrific. They're a perfect analogy to help everyone, professionals and users alike, to really intuitively understand some very complex systems and easily make good decisions. It's easiest to start at this end of the timeline with the raincoat envelopes, which are really get going after the First World War, probably because that smashed the old masters and apprenticeship systems for passing on knowledge. Raincoats are based on the idea of a waterproof layer that using materials that are more or less impermeable, things like glass and metal and cement and engineering brick and plastic, all of which take masses of fossil fuels to make. When the water hits the raincoat, it just beads and it collects and runs down under gravity, and eventually it hits the bottom of the raincoat where it can soak in and create moisture problems. To make things worse along the way, it has to contend with the joints, and making these waterproof is really complicated because raincoat materials also expand and contract a lot with temperature change. So even something like cement or concrete, which you can smear over a large surface, still needs expansion joints or it will crack, unlike lime mortars. Actually, it'll probably crack anyway, and there'll be fine cracks too. And fine cracks and joints in raincoat materials make brilliant capillaries, so they suck through liquid water. And the pain is, the harder you try to squeeze two surfaces together to seal them, the thinner you make the capillary. And the thinner the capillary, the better it is at wicking in the water and moving it about. So making a joint that can take up movement and still stay waterproof is super tricky, especially at all those really complex corners and interfaces where you get lots of different planes meeting up. It's a nightmare. All this means if you're going to stop rain getting into the interior, raincoats generally need multiple layers, and all that layering makes them tricky to maintain. The obvious examples are flat roof. If you've got cooling water, it's probably going to wick in somewhere. And once it's inside, it's going to be moved about between all those raincoat layers. So it might appear on the ceiling a long way from where it came in. And that means locating and fixing leaks can be an interesting challenge. And there's another problem with raincoats too, which everyone knows about who's ever worn a plastic Mac in hot weather, or if the rain's got down back your neck. Once the rain's on the wrong side of that waterproofing, it can't get out again. And that could be penetrating rain, but it just could as easily be water from building use, condensation, or increasingly things like plumbing leaks. Since raincoats take a lot of energy expensive materials and are tricky to maintain, I guess it's no surprise that the pre-carbon way of making building envelopes was completely different. It was greatcoats that are mostly or completely made of porous and permeable materials. Actually, we don't have a good word to describe how they work because permeability is about saturated materials under pressure in a lab. And that's obviously nothing at all like the situation you've got in a real wall, where it's certainly not going to be dry, but the pores aren't all going to be filled with water either. So what you've probably got is some fine capillaries full of water, lots of pores full of air, and lots with a bit of a mix of the two. So what happens when a raindrop hits a wall like that? Well, it's held in the surface pore it hits until it evaporates. It doesn't collect and flow down, and it doesn't get in further. Because of the air, it's trapping in the pores behind it. Air and water don't mix. It's the difference between putting a brick in a tray of water where the air in the pores can escape and evaporation and capillary action can then pull the water through so the brick saturates really quickly, and dropping the same brick into a bucket of water so that the air in the pores is trapped by that water and the brick will take weeks or months to saturate. And a brick in a wall is actually much more like a brick in a bucket than it is a brick in the tray. The only time a raindrop's going to get sucked into a greatcoat is if the pore it happens to hit happens to be the mouth of a capillary that's already filled with water instead of air for some reason. Usually it's something like a gutter leak or a flashing leak, letting water into the wallhead, or these days a plumbing leak. Then the liquid water that's already there will entrain it. But as long as your building's in halfway decent condition, that's not going to happen very often, which means that the key to keeping a greatcoat enclosure working isn't at the surface, it's at the building scale. It's making sure that all that protective detailing is there to stop the rain getting into the fabric so you don't get too many capillaries filled with water. So all those wide eaves, gutters, flashings, hood moldings, sills and drips, renders and lime washes, and so on. And vernacular architecture worldwide is characterized by these features because they work. Having water filling some of the capillaries out onto the surface isn't entirely negative, actually. In fact, it's critical to humidity buffering, the ability of greatcoats to modify swings in humidity. That's all about the water-filled pores at the surface, grabbing hold of the water vapor from the air when it's humid and letting it go again by evaporation when the humidity drops. If the fabric were perfectly dry, it wouldn't buffer, as Tim Padfield's shown. But since any real wall is never going to be dry, we have a naturally great system. If water does get in too, that same system of capillaries can draw it out to the surface again so the wall can dry. We do need to remember, though, that the drying process itself does create more water-filled capillaries to the surface. So if your building's a bit neglected and water's getting into the core, then it's more likely that rain hitting the wall will be drawn in, and that creates more moisture-filled capillaries, so it's a bit of a vicious cycle. But even a very neglected building can dry out again. Once the source of that water is found and fixed, we've got plenty of evidence of that. Where we really get problems is when someone tries to turn a greatcoat into a raincoat by covering a wall with something like a cement render or a plastic paint or a hydrophobic coating. The rain runs down the surface, then whenever it meets a small imperfection, crack, it's very likely to be sucked in. But the coating slows it getting out again, so the wall gets wetter and wetter. And of course, any water getting into the wall from any other source is also trapped. It's really common to see blistering because the coating makes the pathway for water to the surface much more convoluted. So water builds up under the coating until there's enough of it to fill the pores and percolate around and find a way through to the surface. Once it gets to the air, evaporation can then draw it through really super quickly. And that's kind of like tugging on a train of sausages, I think. The speed of evaporation breaks the liquid flow path, and that stops drying until you get enough water building up again to repeat the cycle. But each time you break a liquid pathway, all the salts that are being carried by that liquid water are going to be deposited. So it's the ideal conditions for salt cycling damage under the coating, which is, of course, exactly what we see. Clearly, the phase change between liquid and vapor is a big part of the moisture story, but unfortunately, there are lots of misconceptions around vapor at the moment, especially when it comes to the models used for some insulation calculations. Not least, there's an idea that vapor can and does pass through permeable materials, so it's worth setting out the reality. With thermodynamics, you can easily show that vapor molecules can't get through porous materials and that the vapor transmission tests are actually recording the transfer of condensed liquid. But perhaps it's even more convincing to get this across to people who aren't BP experts if we just set it out in first principles. So when it comes to vapor transfer in free air, it's of course absolutely the case that water molecules move from areas of high pressure to lower pressure. That's just the natural result of collisions over time. But I think there's a common misconception out there that individual molecules somehow make a beeline for the lower vapor pressures. It's inherent in the Rowley-Glaser model, which suggests that vapor pressures on either side of a wall will drive vapor through the wall. Well, I guess if you're thinking of the big voids in rain screen walls, you might get some mileage of thinking of the movement of vapor from void to void through big gaps. But it's not useful at all for water vapor in pores, even when it comes to the so-called vapor permeable membranes. If you imagine a water molecule in the air that happens to travel into the pore of a porous material, it'll keep going straight until it hits pore wall, and then it's going to lose some of its kinetic energy. If it doesn't condense immediately, it'll bounce off and head in a different direction until it hits another part of the pore walls, losing more energy. So condensation happens really quickly. Vapor getting in from the exterior is going to condense within the first pore or two from the surface. But of course, that molecule might attach to other condensed molecules or water that's already in the pores. And then the resulting liquid can easily be moved around the pores by capillary action and gravity and percolation. And it might even be drawn right through the material and then evaporate out the other side. This is what happens with driving rain. But it's only going to move in the liquid state, not as a vapor, no matter how thin or how porous the material is. If you compare the tiny size of a water molecule to even the thinnest Gore-Tex membrane, even if the molecule is somehow magically going to travel just in a straight line through the material without colliding with anything, which isn't going to happen, the straight distance it would need to travel is equivalent to a person walking once right round the equator. So if you could look inside the pores, you'd see molecules evaporating and condensing all the time, but that's going to be completely independent of the conditions outside the wall. The water vapor will, inside a pore, inside the wall, will only see the immediate pore walls and the contaminants, only its local environment. The relative humidity and temperature out in the surroundings and the air movement aren't going to have any effect. But if you've got liquid flow paths connecting to the exterior, then the exterior conditions can certainly drive movement of water. And that's not just semantics. The difference between liquid and vapor is critical for understanding drying, because to get water from the core of any material out to its surface, what you need is an unbroken liquid flow path through a capillary or interconnected pores. Just like overcoming the barrier of the surface coating, the moment you start to remove water from the surface faster than it can travel to the surface from the core through what's probably a pretty tortuous pathway, you risk breaking that liquid flow, and then drying is essentially going to stop until the natural processes like condensation and percolation have reestablished that liquid continuity again, hence stage 1 and stage 2 drying. Which is why building performance expertise is critical for explaining to impatient clients why slow and steady actually wins the race when it comes to drying walls after flooding. The realization that models like Glaser are quite wrong in terms of the physics, of course, does raise the question of building membranes and what it is they're meant to be doing. And I think the answer is it's often unclear what their intended purpose is. People are adding them in just in case, which is actually really dangerous, and especially for greatcoats. And even when the purpose is clear, like keeping rain out from insulation, it's not necessarily quite so clear that they're really up to the task. Perhaps with enormous care and attention to detail, you might get a couple of decades out of the best of them. But what does that mean for care and maintenance? How would you know when this membrane was starting to fail, and what would you do when it did? So for me, that raises an important general point, which came up yesterday too. For all materials, old and new, that we might want to use on a building, I would argue that as a minimum, we really have to know as much as we possibly can about its failure modes, so we can say whether or not it's the right material to use in any particular case, and then what we need to put in place for future care and repair. Leaving this to the manufacturers just won't cut it. It needs building performance expertise to see how any addition behaves as part of a system out there in the real world. The big reason we're so confident about traditional materials and systems is that we do understand what makes them fail and how to prolong their lifespans quickly and easily. So having established that greatcoat systems do work brilliantly, you can understand why they were the only way of building envelopes until very recent times. Raincoat materials like lead sheet first appeared very rarely and were used very sparsely. One of the things that's so striking to modernize in about this timeline is how terribly late glass comes in as a material. It's so common to us now that we assume it's always been there. There are some really excellent reasons it didn't appear earlier. The chemistry and technology are incredibly complex. But the essential problem is how much energy manufacture takes. That made it phenomenally expensive. And for the first few hundred years after window glazing was invented in about 900 AD, it was pretty much exclusively the property of the church. But you see those medieval builders learning and innovating incredibly quickly in response to these new building problems they start to meet when they introduce a raincoat material. In very short order, they invented all those building features that really characterize the Gothic, all made very decorative, but they're all there for a really practical purpose to keep as much rain off that glass as possible. They also, of course, got new problems of discomfort for the occupants, especially downdrafts caused by the interior air being chilled where it met the glass. But they worked out very quickly what to do about that too, as we know, because we have thousands of wonderful medieval images to show us, even though they never actually bothered writing it down, because it was something every day. It made simple common sense to them. But before I point out to you exactly what it was they did, we need to dive into some medical science, as I promised. And it's thermal physiology, how we physically interact with our surroundings to keep our metabolic processes working properly, to keep us alive, in fact. We in the buildings world seem to have developed some really weird ideas around this over the past 100 years or so. So again, it's very much worth going back to basics. And the basic thing is that we aren't like cups of coffee, just passively losing heat into our surroundings until our skin's at the same temperature as it would be if it were just thermodynamics, although most of the modeling assumes that's how it goes. Actually, we're warm-blooded, and like all warm-blooded animals, we're the heat source. And we evolved an incredibly complex thermoregulatory system designed to turn most of the food and oxygen we take in into heat to keep our vital organs at exactly the right temperature to work properly. If the brain, the heart, the lungs, and so on go outside a really narrow temperature band, it's less than a degree either way, the cells start to die and so we die too. But since we're continually generating heat, we will always need to be losing some of it, even if it's very cold, just not too much. So we have all incredibly clever control mechanisms for getting that balance right. And it's a dynamic balance. It's changing all the time as we move around, as our surroundings change, as we do different things. Thermoregulation is really complex and involves all parts of the body, but a lot of it's centered around the skin, and especially the blood, which carries heat around the body as well as all the nutrients. So the reason our hands and feet feel cold in cold conditions is because they're cooling fins. The blood in them is easily chilled. That's really great if you're too hot, but if you're losing too much heat, the body reacts to that by pulling the blood back from them, which is why they get so cold and why they look blue. The science of exactly how we lose heat into our surroundings is super important to all of this, of course, and we lose some by touch. How much depends on what we're touching and how much of our body is touching it. We lose some into the air, mostly by evaporation from the skin. So if you've just jumped naked and sweating at night out of a Finnish sauna in the middle of winter into a stiff breeze, then you might perhaps lose close to the maximum you could into the air, which is still less than 22% of your total heat loss. But into the indoor air, it's more like at the minimum. It's just a few percent, even when the air is very cold, which leaves the $64,000 question, where was all the rest of it going? And well, the biggest way we lose heat by far is by radiating it out into our surroundings. That's at least 60–65% of our heat loss. But if we're wearing light clothing and we're surrounded by surfaces that keep absorbing our heat, glass, metal, stone, that can go up to as much as 80–85%. So at the moment, we concentrate pretty much exclusively on that tiny amount of heat we're exchanging with the air, even though radiant loss is infinitely more important for comfort. Currently, though, it's almost entirely neglected in the way we design and the way we operate our buildings in the global north, which is all predicated now on controlling the air temperature. But that's a red herring. Pre-carbon, they took an entirely different but extremely effective approach to thermal comfort that was almost entirely passive, which is our cue to introduce the strand of history. Now, in the pre-carbon past, no, they didn't use fireplaces for thermal comfort, except incidentally. That's a post-carbon idea. It's Victorian and it's perpetuated by a million video games and television programs. The genuine medieval images show us the enormous fireplaces being used for tiny fires for cooking. They are that size to make sure they got rid of all the combustion gases. And when they're not used for cooking, the pictures show us they were sealed over with panels and settles and cloth. Now, we did get a bit of a blip in the UK of energy being used for heating when the Romans came to the frozen north. They didn't know how to build for the British climate, and they didn't know how to dress for the climate either. But instead of following the natives with their trousers and thick earth walls and those passive tricks that I'm going to get onto, they decided to try and transfer the hypercore system from their bathhouses back in Rome into their ordinary villas in England. The Romans are just so much like us in so many ways. The original global north know-it-alls, addicted to technological solutions to non-technological problems. They used so much charcoal, burnt so many trees to run this. It was really completely unsustainable, and it actually won't have worked all that well. So it's no surprise that when the Romans left, the locals went straight back to what they'd been doing for centuries. And what they were doing and kept doing was this: slashing that huge component of radiant loss directly by just putting up simple barriers between their bodies and all the heat-absorbing surfaces around them. They used draperies and canopies and rugs that could be put up in winter and stored away in summer when some radiant heat loss was actually really useful. And not necessarily over all the surfaces, often just where people were sitting working quietly. Even better, the draperies weren't one-trick ponies. And I think when energy is costed properly, I don't think you have one-trick ponies. They were at the same time, they could be using them for draft control to stop or channel air movement, that next big contributor to comfort and discomfort. And that's what they did with those new glass windows for the churches. They hung their wall draperies right across the bottom of the windows to catch the downdrafts, which is why the medieval windows have such steep internal sills, which used to puzzle me. And all this drapery was clearly effective. By slashing that biggest contributor to thermal discomfort without worrying about air temperature, they could and did open their windows even in winter. And we can see that from the paintings. That's exactly what they're doing. And we also know from what they wrote that masses of fresh air was exactly what they wanted too. And this all fits with the latest research from the thermal physiologists who've been showing people are much healthier if they're exposed to changing thermal conditions. That can reverse not just obesity and blood pressure problems, but even type 2 diabetes. So it's probably no accident that the increase in these conditions in the global north mirrors the increasing control of interior environments. And if that's not enough, the thermal physiologists are also pointing out that we're more comfortable too if we're exposed to more changing conditions, because the thermoregulatory system is use it or lose it. So if you pickle yourself in controlled conditions all the time, it closes down and it takes a while to start it up again. And if it's not working, that means you feel all the slightest changes in your thermal surroundings that a well-functioning system would just neutralize without you even noticing them. And anyone who's ever been camping knows that really well. For the first few days, you feel every change in your bones, but after that, you barely notice them. And that's not psychological, it's physiological. But what happened to the draperies? One minute they're everywhere and the next minute they're pretty much forgotten. Well, I think a number of things are happening at the same time. And again, fossil fuels played a really strong role. First of all, they disappear around the time of the Great Plague, and people did know that the spread of the plague was associated with fleas, and that gave draperies a bad name. It must have also made them unfashionable. They'd probably have come back again, but this is the century of the Industrial Revolution and the Enlightenment. So first of all, they'd started to make glass with coal, which made glazed windows affordable. So building envelopes started to change dramatically. But unlike making bricks or lime, making glass wasn't a local activity. It needed not just masses of energy, but also special materials. But they had the new canals, which meant they could transport the coal and the sand and the other raw materials from one place for making the glass, and then they could send that finished product off far away to market, no matter how heavy it was. And of course, glass is heavy. But all this meant that glass had to be made by a company, an entrepreneur, and that commodity-led approach to building is something quite new. And I think it's terribly important for us if we're going to really understand that story of that history of energy in buildings. By the end of the century, they'd worked out how to make iron and steel with coal too. And once they had, we were really often running on a high energy journey, because with iron, you could dig more coals and canals, buy more coal, make steam engines for manufacture, steamships, trains for transport, and the money rolled in for the new industrialists. But they needed people to man their factories. So they cajoled and they bullied them off the land and into the towns. And then those people needed housing. So that expanded the market for the new building products. And the new entrepreneurs started to look for new ways of making buildings that would create more markets for their materials. And so it was out with the old and the tried and tested and localized and well understood, and in with the innovative and product-centered. And finally, you have the beginnings of the fashion for technological solutions. Beforehand, nobody much cared about air temperature, because from experience, they knew what was causing their thermal discomfort and they knew how to fix it. But at the beginning of the 18th century, Fahrenheit had invented that first practical thermometer, and that caught the imagination of the scientists and engineers of the Enlightenment, who cast around for ways to use this brand new toy. And they developed new theories of comfort, and finally all sorts of inventions intended to heat or cool the air. And of course, even with the wooden paneling, without those draperies and rugs, but with big windows, the houses of the 18th century must have felt pretty cold. Count Rumford's grates appeared at the very end of the 18th century, and they were the first fireplaces to be aimed squarely at thermal comfort rather than cooking. They immediately became incredibly fashionable, and rich people put them in every room, adding massively to London's smog. But they also must have made the houses super drafty and even more uncomfortable. So I'm not surprised the Victorians put lots of drapery back again, or they seem to have thought it was just for controlling the drafts. But like us, the Victorians were modernists and gadget fiends, and like us too, they took a weirdly romanticized view of the past, and in the name of archaeology, stripped back the pre-carbon buildings to their shivering bare bones. They stripped off all the lime renders that kept them dry. They even pulled out the ceilings that kept them warm and passively lit, and all the other critical fittings like the draperies and paneling and box pews. And then they added in things like coal-fired stoves. But because the hot air rises, air heating has all sorts of unintended consequences, especially in tall spaces like churches, and especially if you've also pulled out the ceilings. You know, essentially, if you think about it, what air heating has to do to stop discomfort is to raise the temperature of all the surfaces so that the occupants don't lose their heat by radiation. Now, I'm not really sure we want this anyway, because it means you have to aim for conditions that suit only one occupant doing only one thing. So you might be able to make it pleasant for someone sitting reading the Sunday paper, but it'll make it much too hot the moment they get up to do the housework. It's a very different approach to what they did in the pre-carbon period. Here you can see the bride, who has to sit still, has a cloth hung behind her on the wall to keep her warm without overheating all the people who are dancing, having fun. You do see early on the thermal physiologists trying to call out the creep of air temperature as a proxy for comfort or health. Leonard Hill certainly knew what he was talking about, and he didn't blow any punches, but he was up against some big market forces. This is the first constitution of what went on to become ASHRAE, and I think we can agree that they succeeded beyond their wildest dreams. So much so that we're now in a world where in the US, it's heresy, just about a lynching offense, to suggest that anyone can live without air conditioning, especially in a warming climate, even though only something like 8% of buildings have it in the hottest parts of the world. And that's also despite the obvious fact that on top of all the issues around thermal physiology and comfort, trying to use the air to warm up or cool down the surfaces is incredibly inefficient and energy expensive because it's so indirect. As the hot air rises, even it'll be evaporating any water out from the walls, so cooling them down. So all that's great for manufacturers and fossil fuel companies. Not sure about the rest of us. The air temperature obsession was codified in the 1970s by Danish engineer Ole Fanger, who decided to try to put a number on the air temperature you need for comfort. Via some very odd experiments, he developed two indices intended to predict how comfortable or uncomfortable occupants would feel under different temperature conditions. Now, the simplicity of that numerical approach, of course, made it wildly successful, especially with engineers, and it still underpins most comfort standards and the way most practitioners, architects as well as engineers, design interior environments. And of course, it underpins our obsession with insulation and sealing up buildings. But there are some absolutely fatal flaws in the underlying assumptions. For a start, that your surroundings are isothermal, as if you're floating in a sphere just made of one material all the same distance away, and that the situation is steady state, which is clearly just about as far from the truth as you can get, and also that everyone's the same, which is also demonstrably untrue. So it's not really surprising. Field researchers quickly found there wasn't much relationship between Fanger's predictions and reality. And Stefano Chavon's team at Berkeley have concluded it shouldn't be used in practice and certainly should not keep underpinning standards for thermal comfort. So you can see post-carbon, our solution to our ever-increasing discomfort became just throwing increasing amount of fossil fuels at the problem. But once that became a problem in its own right, buildings were increasingly sealed up, leading to serious problems of indoor air quality. And again, the solution was hunted for in technology rather than science. Already by the late 19th century, alongside all the new materials and innovative structures, new building specialisms were cropping up all over the place. And we've already talked about this. It led to the increasing codification of building. And as the 20th century wore on, the codes became increasingly fixated on manufacturing practice rather than end results. The British standards used to be very clear in their small print that that's what they were about. Manufacturing standards, not best practice. But looking for the old quote, I see that on their new website, that distinction's been entirely lost. And that's terribly dangerous when buildings tend to be now assembled from product catalogues. We can compare this to the feedback loops that used to exist when you knew your builder and they probably lived a few doors away. So if something went wrong, you hauled them back, hammered their head on the wall and said, fix it. And that's how we learn, and that's how we pass that learning on into better practice. So we're now facing the inevitable results of our own very different and very siloed approach. Well, you know what they say about repeating the same thing time after time, but expecting a different result. So I reckon it's high time we stopped, took stock, and considered the wisdom of going back and learning again, not just from our own pre-carbon past, but from ongoing practice in the Global South, which still has a tiny carbon footprint for just those reasons. And our colleagues there can tell you too how very much the pre-carbon approaches to constructing, operating, and maintaining buildings have to contribute to healthy and happy societies. The great thing about getting away from fabric first retrofitting and focusing instead on people first is that all those pre-carbon passive systems don't just use very little energy to make and absolutely none to run, but unlike focusing on air temperature, U values, insulation, they fit with the science and they go right to the heart of what's actually causing an individual's discomfort, so they can easily be tweaked for everyone's benefit. You can make cozy corners for the people who are sitting quietly, but without making it all horribly uncomfortable for the other people sharing your space, but being active. And even better, you get an instant improvement, which is really important for comfort. It's all about crises of discomfort, being able to do something immediately to sort that out, which isn't to say that modern necessarily means bad. Of course, old isn't always a synonym for good either. They came up with silly ideas in the past too, like parapet gutters. And plumbing's great, even if we aren't yet very good at it. I'm really interested in the potential for replacing window glass, which is a massive sink for radiated body heat, whether or not it's double glazed, with Persipex, which is not. It's a material that could really be a game changer for comfort and prove worth its carbon cost. Ceiling fans are terrific. They're so much better than traditional punkawallas. And what about all those wonderful modern tools for warming people rather than the air, like heated blankets? These work so well, and they're much safer than the old open flames or hot charcoal. And if we can run these people-centered things directly from renewable sources, then we'll really start to be getting to a better place fast. But the key is to start listening to our bodies again instead of reading thermostats and actually working out when and why we feel uncomfortable in our particular buildings for our particular ways of living in them. And from that, finding new low energy or no energy ways of dealing with the root causes. Bill and I are currently involved in the really exciting project being run by the Sheffield Diocese by Katie Steele and Amy Graham at Cherubim. The PCC members who are our co-creators might not be building experts, but they've had no trouble getting this different approach to comfort and discomfort and have been setting up their own trials and experiments with brilliant results. It's the same as Freya Wise found in her PhD results in Cumbria, that occupants who really understood how their building worked found ways of operating it that used scarcely any energy. So that's another vital role for BP expertise into the future, finding the ways of helping people to understand their buildings and learn how to sail them again for themselves and their needs. It's the holistic viewpoint that counts. Well, that's all covered a lot of ground, but I hope you can see how it all hangs together, and that having a building sector grounded in a deep understanding of building performance, of history and science is absolutely key to solving the problems facing our world. Everything we do in and around buildings, so we ain't going to get anywhere we need to be unless we put the built environment front and center in our understanding of the causes of climate change and environmental destruction, and don't blithely keep entrusting solutions to the market. But it's also clear that building performance shows us much simpler and faster and safer ways of making a really sustainable built environment and therefore saving the planet. And that's why I was so excited at this wonderful gathering being organized by Hutton and Rostron and Socotec. And I'm really hoping we're going to seize the opportunity to set up a really effective network, not just to share our knowledge and discoveries and pass them on to the next generations, but also to influence policymakers. And we need to do it quickly. We mustn't let ourselves be siloed. Our strength is in the diversity of backgrounds we bring together. This doesn't and mustn't sit in a siloed space, which means developing expertise doesn't belong to any one professional field. What BP experts need to be good at this is magpies, collecting information from all over the place and bringing it together and making clever connections. Or perhaps a detective, to quote wonderful Fred Masham Lee again, a surveyor only needs 3 tools, 2 open eyes and 1 open mind. Most importantly, we have to really stop fighting on the enemy's ground, to stop arguing about the U values and the technology, and start focusing clearly on the science and the history and indeed the economics. And we also need to get beyond preaching to the choir to find some way of getting our messages out to the rest of the world, influencing education policy, all the degree-based professional associations, but also perhaps even more importantly, ordinary builders and everyday occupants managing their buildings. To make our voices loud enough, we need to be communicating in a clear and coherent way. But luckily, as we've seen, the messages from first principles science and from history do turn out to be simple and logical. They just make sense to the people hearing them. So let's get the word out and see whether we can't save the world. Thank you.